Guys, it's melting.
Say. It's really time-based. It's time-based. It's time-based.
Are they gonna turn off the lights or? I'm a bit shy. Okay. Hello everybody, we are Team Quadrant. Doshkan Aladat, Tahel Shahar, Wei Chenye, and myself, Juan Montiel. We are presenting our project, Instant Ice, which explores the idea of using a swarm of quadcopters to 3D print with ice. So looking at the precedents, flight in architecture is not a new thing. During the 70s, architects envisioned the city of the future as a multi-layer system where flying transportation moved at different heights through a vast network of interconnected spaces at all dimensions. The Broadacre City by Frank Lloyd Wright, it's a project which envisioned suburban spaces where people would travel in personal helicopters. Later, Buckminster Fuller developed a way to deploy geodesic domes for army compounds. And most recently, the flight assemble architecture installation by Gramazio and Kohler shows the potential of using distributed systems in construction. On the other hand, 3D printed is a new and exciting manufacturing technique. It offers a huge array of benefits. You can print infinitely complex and varied objects. You don't need any assembly or skills, and the materials are manufactured directly on site. Other precedents of large-scale 3D printers, such as the D-House and the Winson company, has shown big promise. For example, this Chinese company is able to print up to 10 houses in 24 hours. And the research done by IAC in swarm robotics shows how smaller robots can print objects much larger than themselves. And in our thesis, we are looking at using a swarm of quadcopters to 3D print large-scale architectural proposals, which are time-dependent due to the nature of the material being used, which is ice. Traditional construction techniques generate huge amounts of waste. According to the DFRA, the Environment Agency of the UK, just in the UK alone, 335 million tons per year of all the industry waste is produced by construction. This is not taking into account the amount of carbon dioxide produced by extracting the material, transporting, processing, and assembling it. So this is why it becomes necessary to search for a material process that reuses the material, and that at the time where the architecture is not being used, it can just melt away into the landscape without producing any waste. And so the advantages of swarm printing would be that it's a system that can build on site, on demand. It requires very little infrastructure. It is temporary, sustainable, and free, and you can produce very complex and varied results without assembly or skills to put them together. In previous ice construction, the most traditional technique is to layer, like the igloos. Also, Heinz Meyer did the sprayed shells, and in the University of McGill, they also casted ice in the same technique as you would with concrete. And if our system is to be deployed on site, it requires information about the environment to tell it what is the temperature, windfall, and the wind. And so we look at the National Oceanic and Atmospheric Center in North America, which provides weekly data about these parameters. And this is our thesis. Swarm printing explores the idea of using an autonomous swarm of quadcopters to 3D print ice in architecture. The system relies on stochastic and deterministic methods of design by incorporating a top-down logic to ensure the project's architectural performance, and a bottom-up approach to account for the logistics and organizations of swarm robotics. It negotiates between material, environment, and machinic behavior to arrive at complex results. The system looks to respond on-demand conditions that require temporal architectural solutions in cold environments. To develop our research, we set up a series of experiments with ice as a material, and using the drones to find which are the constraints, and then fit these parameters into a simulation, which would allow us to speculate on a bigger scenario.
Since our thesis is situated in the cold area, we start to seek the possibility of printing ice, which is also a phase-changing material. We first tried putting different types of water into the freezer and time how long it freezes. While monitoring the temperature, we realized the temperature of the purified water can drop to below 0 degree without being frozen, which is a scientific term which is called supercool water. When supercool water hits the cold surfaces, you will freeze instantly. We managed to stack up the supercool water in room temperature. After gaining the better control of the supercool water, we achieve some structural typologies such as cantilevering ice become ice bridge, branching columns, and dome. So this one is the branching column. And domes. And the different structural typologies.
We created phase change in simulation, determined the condition which water freezes, linked to another particle, and turn into ice. We simulated the melting process where the link between the particle decreases and the velocity increases.
During the process of printing, we realized not all supercool water is being frozen when it's landed on the previous layer. As a result, the bottom part of the geometry will become thicker. In a sense, it's good for structure. Since we don't have a simulated cold environment, we decided to work with sodium acetate as a replacement for the prototype. Sodium acetate has a similar material behavior and material property as ice. When this oversaturated liquid hits the crystals, it will activate the crystallization. For the material deposition system, we came up with two options, which are the servo control tab, on and off, and the pumping system. We decided to go with the servo control purely based on the gravity because of material sensitivity. There are several criteria to address. One is the rotation of the tap controlling amount of water, the attached nozzle for the better deposition quality, and height and speed of the nozzle, which determine the stacking rate. So this is the evolutionary of modification of tap and nozzles. And we tested the height and the speed. This is the height and the speed manually to see how it affects the material printing width and the thickness. And we're going to pass that knowledge when we're attaching the nozzle to the machine, the CNC. Once the mechanism is working, we start printing columns, whether it's done by one-point deposition or circular movement to achieve using minimum amount of material to achieve the maximum height. And we printed a 1-to-4 wall section with sodium acetate. And the photos. Okay, this is a cool video. At the end, we ran a large freezer and can operate the cold environment. We managed to print 1 to 2 prototypical ice wall with the height of 80 centimeters, which is the ice wall you see in front. We set the temperature to we set the temperature to -5 to -8 degree, and the ice wall takes about roughly 500 liters. Again, we pull out some detail from the previous successful experiment, cantilever bridge and branch. So then photos of the ice walls.
Because of the unpredictable nature of the material, we also decided that it was necessary to set up a feedback system. So we use a Kinect to track a 3D point cloud of the material and feed that information directly into Rhino, where we correlated the scales were exactly matching with the real life version. And after we developed that first prototype, it was necessary to get some kind of a machine control. So we did a series of tests to see how we can sustain negative space, find out the rate of deposition, the tolerances, overhangs, the surface quality, and the machine speed necessary to print an object.
So based on the experiment, we analyzed the cantilever curvature by dividing them into layers based on the material thickness. And we realized the angle cannot be over 45 degrees. And this is an attempt that we try to increase the layer thickness when the angle is decreasing to below 45 degrees. So we conclude that the distance between the slicing curves shouldn't be more than 2 millimeters.
So after testing the first prototype, we became quick to realize that we had to find another solution because we couldn't make any negative spaces to turn off and off the machine. So we put a solenoid valve controlled by Arduino and a nozzle, and we could start to have these kinds of objects which were written through a custom G code and fed into the CNC. And these are the results that we had. After that, we started like on parallel research about the quadcopter, and we were using this one, which is an F550 flame wheel equipped with a Pixoc autopilot, and we needed to have some sort of position feedback. So we started looking at this system where one uses a camera and a sonar to detect local position, and the other one uses external observer, which is infrared cameras. And we perform a series of flight paths to test the accuracy of the quadcopter, such as flying in a straight line and getting its position into the computer, flying in an L shape, and simulating these behaviors, flying in a circle. This one is creating a polygon, holding position. And this one is doing point search. Then we tested the attachment to see if the quadcopter could actually carry it, which is the one, it was the first prototype. And of course it has some problems because it's a liquid material, so it requires more algorithms to hold it in place. And this is the prototype that we are currently developing, which takes the same pieces of the other quadcopter, but it also has an embedded material tank of 400 milliliters and all the necessary components that we attach to the CNC.
To develop a design strategy, we have developed a series of simulations in order to utilize a multi-population of UAV drones and their behaviors in order to achieve an architecture that's strategized by time, economical in energy, and all the resources that have been spent. So these are the range of simulations that we have developed. We have developed deposition simulation, material collection, melting, swarm printing logistics, population and speed, and detailed material organization. So we started with deposition simulations, which are fed from the actual material results in order to arrive in some conclusions and feed them into the simulation, such as how long would it actually take for a certain volume to print, and how we can use this knowledge in the simulation so that we can design with it. So that looking at the morphology of the aggregation of the material, first we have roughly developed a particle spring system, which acts like the actual phase state changing aggregating material. Then we have introduced temperature as a virtual variable in the system and constantly checking the volume of the deposition. And the temperature has an effect on the actual accumulation of the material, and it has a role in the simulation. So then the simulation is responsive to the dynamic temperature change, and then the agent can be also responsive to the height of the material. So when it's cold in the virtual environment of the simulation, the aggregation of the material is much faster. But calculating physics all the time is very difficult, and especially in architectural scale. So we introduced a voxel-based approach to this material system, so that it can have all the benefits of the previous system, but it can be faster and more fitful for high populations. So there is a voxel system, and it has an additional advantage of being able to assess the density because it's an outside global system. So having this rough information about the deposition and volume and time, we tried to do another test with this knowledge. So we have prepared the scale simulation, took the drone in the actual scale in the simulation, and took all the parameters from the real life. So, and we tried to build some very simple architectural primitives, keeping track of energy, keeping track of material, keeping track of flight distance, and of course keeping track of the material boundaries using the voxel-based system. So we can have an idea to design further. And in this set of tests, we just increase the population of drones in a certain trajectory, so that what happens up to what point an increase in the drone population, UAV population, actually helps speeding up the construction. So the experiments show that after a point, of course, the overpopulation of drones causes congestion because they are trying to avoid each other. It's not much of a problem in a large geometry like in the up diagram, but if the geometry is really small that they're trying to print, the problem is even worse. So where does drone take the material? So we had to introduce a ground unit which we assume that has material and energy that the drone is going to pick up and refill itself, because it has to be light and it has to be agile. And material has to be processed and has to be in a certain temperature. This unit has a certain awareness of its resources. So we tested how to distribute this unit around certain trajectories of printing and what is population and its distribution. And of course, as common sense says, it's a homogeneous distribution around any trajectory is better. So we introduced this step into the ground units, which they are equipped with the capacity to arrange themselves and optimize according to a geometry task to print. And even they have an awareness of where the drone is and can actually follow the drone's position. So there are two groups of agents constantly in dialogue with each other. And if we test these three optimizations between each other, we see that although it brings up additional complexity, the dynamic movement of the charging stations, which is on the bottom, really adds up to the project, provides less flight distance, therefore less time to print. So in terms of providing material to the ground unit, we thought that why not this ground unit be a material collection in itself, because it's already on the ground and material has to be processed. So we prepared some search algorithms for material collection and developed different behaviors so that they can collect from a certain perimeter, keeping a certain area untouched, or they can travel to a certain area and just collect the material in that position. And this is a further developed version of the system which has a certain awareness of the material resources and which areas are available to search, which are available to build on, and what is the density of the material. So that as a tool, at the end to design with, we had a simulation that can keep track of the material density on site, printing density, has dynamic charging positions, having an awareness of the material. Drone UAVs has an awareness of the material, and all the system is working for a purpose and giving us a lot of information. What? Okay. So this is an animation of the actual drone and how the charging position this look like. This charging position is an actual machine. It's called Terra.
Yeah.
It's called Terra, so it's a real robot designed for this environment. And it's just we want our UAV to have a dialogue with it. And this would be an animation of how would they behave during a construction of a prototypical task.
In order to overcome the challenge of wind condition and extreme climate condition, of wind and low temperature in cold areas, ice enclosure were explored. The correlation between thermal efficiency, wall thickness, temperature inside the spaces is also determined by the number of users that occupy the space at the same time and over a period of time. We determined the relationship between the size and the spaces, determined condition, and the number of potential users by exploring 3 sizes of spaces, determine their height, number of users, wall thickness, and temperature. The small spaces is for dwelling, and its temperature can reach up to 16 degrees, where the temperature of the environment is far below 0. The second space is a social gathering, and its temperature will be around 5 degrees. Where the large ice enclosure is a multi-dome structure, which has a long life expectancy of up till 3 or 4 months, and can form as a cluster of spaces. In a Okay. I guess. In a constantly changing environment, the ability of modify and implement strategy is highly important. We used metaballs as a generator of urban configuration, which have a dynamic movement, can separate and connect, shrink and expand, multiply themselves, and travel and create double layering. We explored the compression structure by using RhinoVolve for initial form finding. We created sequence of we created the sequence of spaces, tested them thermally, and modified them by adding partitions, located the small spaces higher, and creating layers and openings. And we tested them thermally.
Okay, so based on that architectural typologies, we looked at how would be the construction sequence. If you look at a very simple dome, the construction sequence should be simple and conventional to other 3D printers. So you have to keep track of the boundary, and you have to be symmetrical if you are building something symmetrical. However, if we come to complex shells that like the sections we are talking about, it's not good to have a flat ending, and it's also undermining the potentials of the system that we use, because we can locally change the speed and behavior of what we print. So there can be another way to finish some parts and pass to the other parts. However, it also has a disadvantage of there is no reason actually to wait for a part to actually finish to start the other one. So our proposal is a system where all the parts of the structure and drones have an awareness of which parts they are doing. So no part is built before the part that it supports. So all the system is running in a full efficiency. So our the geometry, we understand the geometry as a series of lines, not as a volume, and on those lines as a series of points. So these lines actually define a certain trajectory for our UAVs to travel on, but we don't want them to literally print something because that's already something being done. But we want them to locally interpret and do something else with it. So we see an opportunity here, and we try to exploit that opportunity of interpretation of these trajectories with agents. So we can give different degrees of freedom for them, for their interpretation of geometry, and we can get different results. So to utilize this opportunity, we have created certain behaviors which you see the very basic versions, such as a rotation, creating cavities, such as a harmonical ribbing, creating structural depth and directionality. And of course, like a combination of both, which a wall section which is rich of cavities and also have a structural depth. Of course, we have tested countless variations of combinations of this, and had a lot of experience with also dynamic rule change and constant rule. There you go. And we looked at how rule change can occur during the process, so that how agents can change their behavior of what they print as they go to the test. So they can make a ribbing in a certain direction and change the direction. They can print a thick thing, then they can go to a smooth, maybe transparent surface. And they can go in a, okay. What happened? Okay, so at the end, we propose a system which can take a simple form, interpret in different ways, and create different results of it according to the needs of the environment, which we call the interpretation. So going back to this cavity issue, we know that the conventional thermal insulation, the cavities are used to create better thermal insulation. So we looked at how our rules, because we are building in a cold environment, how our rules can contribute to that. So increasing the speed of rotation of the agents causes walls having more and more cavities, of course spending more material, but having a higher thermal performance. And looked at the issue of porosity and openings. So how we can utilize the vertical speed versus horizontal speed issue, so that we can create different surfaces which can be used architecturally for real. Then we created a porous wall, although it has a continuation to each other. I think there's an experiment with that on the real wall as well. And anyway, so this is the different level of porosity tested on a larger structure. And we see that the density of the all is different. And the voxel system we developed in the beginning can keep track of the actual density. So this density actually, because it's the ratio between surface to volume area, it can be used to predict melting. So that the more porous we print a geometry, we can say that it's going to melt easier. We can use that information, and we can use that information to be safe in melting. And this is like the catalog of the different behaviors, like as a tectonic, you can see. And this is also a prototypical shell, which has a 3D print there, reflects our process. So it's a simple geometry set given, interpreted by certain rules, and and become something else.
This technology. It's not. I don't think it's. Okay. We explore time adaptive configuration, creating space on demand that can change according to the number of users, the purpose and the environment condition, and the construction process, and demonstrate a structure that can be built in stages according to the need of spaces. So our system is subject to fluctuation and harsh environment condition, which habitation is temporary. For purpose of demonstration, we chose Greenland as an example site. We distribute the spaces with the different sizes on the landscape according to the landscape trajectory, where the base is an energy point, creating spaces in different degrees of enclosure, from a well-protected area to semi-open spaces. And we use h.mov for the initial form finding for the structural configuration of a structure that can be built in 3 different stages. This is the start of it.
Yes.
So this is a site that we choose in Greenland,
House system.
and where our system will arrive.
Will be deployed.
So start talking.
So the system initializing, so there's an initial scan of the topography and path finding for an optimum position, multiple printing behaviors, and charging positions constantly in dialogue with the agents to complete a complex task. So we finished the first stage, established the production path of the second stage, and can initialize the second stage. Green indicates the flight path patterns. So it gives us some information. And we see that we are constantly carving the topography because we are extracting the material necessary for the building to be built. And the third stage has been initialized. Different colors we see represent a decision of different behaviors of printing. So it's a very, very long process, so video has to be really, really fast. But this is the process ending, and the agents are called back to the ships they were deployed. And this is the architecture.
They created.
So interiors are having light and different degrees of porosity thanks to the system.
Okay.
So after that, although there is no much deep work into it, there is a study of predict the melting of the structure. As we strategize the density of the material from bottom to top, we could strategize that it will not melt in a dangerous manner, so it's going to melt from top to bottom.
So this is the different stages of construction. That it will start closer to the bay and continue expand, but of course the form will can change over time because of the melting process. And we chose to build on a slope. Since the landscape can use to create a wind shield and block the wind while the printing process occur and preserve the heat within the inner spaces by creating double layers and maintain higher temperature in the inner layer in order to maintain heat between the spaces and control the amount of air coming into the spaces. Which can dramatically change between the interior temperature and the exterior temperature by editing layers and different levels of porosity. So our system is basically have three layers: the dwelling, the social layer, and the bigger layer of the circulation, where the path, those are the area where the ground agents are traveling and starting to during the construction.
So if we take a little slice from the actual result, here we see how we mapped these behaviors into the trajectory of lines of something desired. So we have a point of density attraction, which we embed agents to perceive as columns or support points, and we also have a surface strategy, which we can build thick ribbing, as you can see, and have little bit of openings, have a really smooth surface and thin and smooth surface, which can make light inside, or has a very grainy and thick wall, which is going to provide a high thermal insulation. And
This is a chunk of the model that shows the different spaces and the different layering. Those are the renders, and this is the showing. This is the end.
This is the end?
Yes.
Thank you.
Thank you.
Show the most recent.
Ah.
You are better speakers than you.
I would say this is the ice model. And we correlate the behaviors that we get from sodium acetate on the ice, because most of the time we were working with this material. Structure in the ice performs much better, but with room temperature sodium acetate. And we developed this series of experiments to try to get a simply closed shell. We didn't quite get there, but comparing it to the previous experiments which were done last year, it's a much better. And the thing is, the structure is holding itself in space by using the surface tension control. So the next drop follows exactly next to the other one, and then over time we start building up. This is the side model. These are some initial behavioral forms according to behaviors. It's a catalog of shells and small sections, and that is the rule.
First, I would like to congratulate you because it's amazing amount of work and very, very, very well communicated. So thank you very much for facilitating our job. Maybe I would like to say that of all the work that you presented, the one part that struck me the most, or that struck me the most, is when you were beginning to build. At some point, you were beginning to build a porous dome, which would be a little bit less of the layered kind of construction, but begin to think about new modes of adding material that are not layer-based. I thought that it was going in a very, very interesting direction there, especially because I for a moment projected that on that porous dome there would be a way to imagine that without your drones interfering in it, that ice would naturally be generated in the porous structure. So it would be a sort of collaboration between what you do as a basic scaffold that is understood as something porous and what nature contributes because of the local environmental conditions. And I have not seen that part of the project, and I must say that I was a little bit disappointed afterwards. Because I really believe that there is a very interesting proposition here that, in my opinion, is treated as if the solution was to do the whole construction with drones and being exhaustive in terms of the materials. And I think that that specific environment could provide something as a contribution that you would not have in a place where, for example, you use clay. Huh? So the fact of using ice, I think, is underused in a way in the project.
I had another material question as well. I think you probably arrived at the conclusion that the denser the ice, the better the structural properties of that ice were. And at the same time, you're trying to work out the thermal properties as well. But in terms of placing it, what kind of densities were you able to achieve against cast ice? And were you getting much efficiency from this method of placing? Were you finding that there was structural problems with the way it was being placed? In other words, were you beginning to get an aeration into the system? If you're casting ice as solid pieces, clearly you're getting a strong material. And how much efficiency were you losing by this kind of method of placing? Was that kind of, were you able to study that or look at that?
It is very porous at first, and the longer it stays in the freezer, because the bits of ice are separated because of the deposition method, but the longer it stays, the more it compacts itself and becomes stronger.
Which I think is probably the first point we were just talking about, and how that begins to bond it together. So there's a process that goes on there from when it's first cast to then subsequently beginning to bond itself almost.
But it's much stronger casting.
Of course, yeah, of course.
I think for me, one of the most sort of fascinating parts about the project is the idea that you're essentially building a kind of cooperative network, an ecology. I love the idea that there's multiple types of units, this kind of service cell that zips around and kind of collects local resources and distributes it in a really intelligent manner. I think there's something pretty incredible about that. And I wonder if you could, well, in some ways begin to kind of even expand on that. I wonder if the capacity for these things to become more complex, that the quadcopter is going to offer you a certain way of, say, depositing material, but there might be another sort of set of robots that are operating, say, on the interior, or there's some other thing that begins to kind of happen because you're so close to, and you're already in such control, let's say, of the medium. You just kind of wonder how far you can take it. And right now you have 2 operators, but there's certainly, I'm curious a little bit now, so you have this spectacular world, right? What else is sort of cooking down there? It's like this, it's a sculptural piece, but I wonder a little bit now about what its potential is kind of further on. And for me, the most fascinating part is just purely the kind of simulation space that you're operating under. And I think I haven't really seen a project that has kind of taken it so far. And it's super smart because you probably couldn't fly quadcopters here or out in the square or whatever. So it seems sort of dead on. The other part of the, I think Marta sort of hinted at it, but I wonder a little bit now, you're dropping material, and I know there's many ways, let's say, to work with water that might not be structural, that might have other kind of capacities. So misting water. I guess I'm wondering a little bit more about the less optimized versions of this, and what are the other things that it might begin to afford. And you get hints at it, especially in the model you're standing beside, where is that actually ice? Is it melting right now? Yeah. You know. Yeah, I mean, there's just so much, so many fascinating things you can begin to think about that you could begin to do with these things. And dripping and dropping, maybe not the right way to think of it. So adding some complexity to the method of deposition could be really pretty fantastic, next step.
Only to add, it's a phenomenal project in really all ways. This ecology of different kinds of drones, the supply, the deposition, I think it would be really great to have a melter, the kind of eraser of the system, which could also help because you're making compression-only structures, but it would be great to have a support medium that you print very low density and then come and melt away. So I think this is really, I mean, only because your project is so great, we can just add little fine details. The other thing which taps into Marta's idea is it's pretty great to have your closed loop system where you're scanning and know where the thing is, so you can adjust for melting that you didn't want and start to come back and fill in. But even much more interestingly, I think, is you have big snow drifts from wind and you say, hey, I could collaborate with that, and then I'm going to completely change my space planning because now I've already got a free wall over here. And especially if you've got plus and minus, so you can kind of do a little bit of carving and a little bit of adding, this kind of cut and fill logic, then it can be pretty amazing, this building that kind of drifts along through the landscape being as efficient in the material deposition or kind of opportunistic as possible.
And there is an area to further explore about the precipitation, I don't know, melting of ice, ground ice, breaking the icebergs from the shores, all sorts of that. So there is a much more complicated ecology that we could communicate to, but it's a matter of time. You know, as far as we are actually aware of the potentials of the system and how would have become a much healthy ecology with the actual environment.
It's a really fantastic project. I mean, I think the last few comments, I think on everybody's mind how this, and you mentioned yourself, the desire that it's not just printing something preconceived. And you introduced the notion of interpretation, which remains a bit vague, and if it's just the kind of randomizing or willfulness and deviation coming to the system, it would be less of an interest. Although a certain degree of that is always part of a search heuristic. So one wonders what is the heuristics of interpretation, what is the aim of interpretation? And a lot of it might be about absorbing contingencies and opportunizing on contingencies with a vague, based on an a priori design, which is a certain, but it needs to be described in a new way, in a different way, with a number of parameters and a number of adaptive capacities, all the things which are mentioned here. We really like that. It's, I think, the vision, the dream of the project we all have, being this kind of ecology which involves all the forces and actors which are already operating on the site, and this kind of harnessing ethos of this project would be the dream of the project.
Yeah, really, congrats, and I like your choice of structural tools. That's the nicest thing or ever done with it. Also, another interesting aspect is, of course, you have a lot of dynamics in your simulation already, but also the wind blowing parts away and kind of partial melting and so on. These kind of structures. In fact, each year in Switzerland, they build these kind of things, and they're looking for more sexy applications. So if this thing can fly more than the 10 minutes that it probably can now, then I think you guys should come and have fun with us in the mountains. So I really like this project. And yeah, come over and let's have some fun.
mean, I think on a lot of levels the project should be commended. But for me, I think what resonates most is, I think it's understated, but the material choices, the environmental impact, that kind of aspect, I think is quite clever. I suspend a little bit of disbelief in terms of technical machines in extreme environments, because I think that kind of conversation is to come. But I think in terms of the way that you've managed, and I second what Jason was saying in terms of simulation, that I think it gives a certain sensitivity to, I think, a lot of the constraints and the parameters that are very much part of this. And as a team, I'd like to recognize the fact that getting that big-ass freezer, putting it in Ching's yard, spending a lot of time in the freezer, is really, really meaningful, because I think you wouldn't be able to actually extract that information and give the richness, I think, in the simulations that you would if you didn't do that. And I also want to commend you on using some kind of very straightforward CNC, G-code kind of stuff to understand basically at the end of the day what you're really working on. It's not a project about quad rotors. It's a project that's really trying to develop an ecology of systems. And the extraction system and the sensing systems and using as much data that people are trying to really understand how these landscapes of change are really, really operating, I think can be enabled. So beyond the printing project, I think that there is something at hand there which is at play, which is how these kind of data mining information systems could potentially proactively work. And so on a lot of levels, I think you guys should be commended. I think when it comes to scenario, like a lot of the projects, we try to speculate on space. And I think if you look at some of the scenarios that happen in these extreme environments, particularly expeditions, and really where the human agency aspect happens, I think that could also enrich what you're doing, because they already bring the equipment out there that potentially could start to co-opt and be co-opted by a system like this to create that, these migratory temporal kind of logics, which really are trying to manage extreme scenarios and extreme kind of life cycles of actually what they're doing. And it has to be forecasted. And it is real time, because at the end of the day, it has to sustain a kind of human agency. To Martha's point, I think it's really important. With all of the different nozzles, you guys have tried a certain family of them, right? And I think one of the things is like extracting precipitation from air, body heat, like you guys are talking about, creating ways of melting the interior to create different kinds of structural logics within what it is that you're building. I think this is also something that you should really tease out, particularly in the document, because I think that sensitivity is there, and the simulations, I think, echo that. So from my side, it's very good.
Yeah, just from my side, I mean, the studio has been really talking about behavioral production, the idea that you compress design and construction within one way of perceiving of architecture, so that one, we can kind of try to take command of as many logistics as possible for the architectural benefit, and at the same time try to improve, say, the resource efficiency and time efficiency of architecture as well. So attacking both the pragmatic in terms of time, material, energy cost, and at the same time trying to allow for more creative freedoms within architecture through managing that process. And in that sense, I think the project was very successful. Like, I mean, I also third the simulation kind of development that has been very strong, and the material development, I mean, we can criticize certain aspects of it, but for instance, I understand that there were some very logistical reasons for some of these decisions, such as due to the fact they could only hire a certain size of freezer room, that they originally wanted to get to minus 30 degrees, but there's no air curtain or anything to prevent it from cooling down to minus 5 at times. They kept the supercooled water, and supercooled water cannot be sprayed easily, because when they used pumps, the water would just freeze up inside the nozzles and things like that. So there's definitely a lot of more work we could do on material, but we also have to manage with the resources we have, and for that I think they did really well. In terms of the simulations, I think there we can see a good emphasis of creative license being used within logistics of the construction process. So that this kind of interpretation wasn't willful. It was always managing very carefully the energy and time resources and the quantity of material. And when we have a material that it doesn't have a density per se initially, but as it goes under load becomes denser. The porosity also enables us to get structural depth with a minimal amount of material being used. So there was this kind of game between void being used for insulation and void also providing for an increase in structural depth with minimal increase in material. So there's some really interesting games going on there that I would say, of course, it's a thesis. They're not, you can't go out and build this tomorrow. But at the same time, there's a creativity that's been shown through those logistics that you can start to see, I think, in things like the structural form finding page. And yeah, so from my side, I commend you for a very kind of broad interrogation of the subject and a very creative license in the way you took it.
Just to add this moment of when you talk about the creative element, or I would say the articulatory and aesthetic outcome, which is there and which is emphasized. And I think I love what I see here in the model. The opaqueness, translucency, transparency, and I think there are ways of manipulating that, and the way you play with, make thematized light. I mean, that's not so much in the simulations yet, but I also like the way the toolpath shows in the way you use the flight trajectories, register as a factura texture, which then gives you the opportunity to say, that's the way I want to make openings by pulling these strands apart. So I think that is an important moment, I think, because it brings it into the discipline of architecture, and where we're doing a lot of proto-engineering in this, we also need to harness and harvest the architectural sensibility on that level, as well as on the social dynamics which are folded into this as well. So I think that's would be I think another chapter in the book of emphasis.
You want to go right on this? Okay. I thought there was an interesting moment in your presentation when you said, and this is the architecture. It was kind of almost as you would want this simulation to do actually anything we could imagine. And I can totally sense that desire. And actually, I got really, stimulated and inspired by this. And we talked before about functionalities, I see them being fulfilled here, manifested in the change of material state. And I think that's also the system intelligence I see in there. The idea, like, that the erasing that was mentioned, the erasing and the dismantling. So my question would be for the next step, like when it goes back to the, let's say, fluid state, and can it be, part of a bigger system? So you take out certain bits to become a certain function and bring it back to the system, a state. Could this be maybe on a different scale and kind of for the next thoughts for this system logic behind it? Could be really interesting.
The one thing that I was going to just add, it seems that the next step, the model space, the simulation space, if you were to, this is a challenge in a way, try and print a perfect dome structure, but do so with a common, like a box fan blowing wind on your quadcopter. This would, in a way, radically change the simulation space and actually potentially make the project richer. It would actually mean that the dome would be, radically skewed, let's say. So your optimal space would need to be, radically deformed, and you would need to understand, and actually maybe you have the fan on low, medium, and high in that process, and have the algorithm begin to respond to local conditions. Because Theo is totally right in some level. We're suspending a certain criticism, because we all know it's an extreme environment. It's a radical environment filled with lots of things that are indeterminate. And so how do you begin to allow your model space to begin to kind of take in that indeterminacy when it's happening pretty locally, right? You'd have things, and that could be a very interesting thing. Just try and print a perfect dome and print it and see what happens, because it could be phenomenal.
This is, I mean,
Yeah.
it's a good comment, and I think it ties to Martha's also about using the environment. I mean, something that some of the other projects strategize a little bit that you'll see tomorrow in terms of the real-time adaptive nature of it. Certainly here we don't see it as it could be. At the same time, the rules that are being engaged here certainly would accommodate that type of thing. And there's the wind environmental conditions to consider, but there's also the, you know, the constraints of the UAVs as well. Like, you know, for instance, the material, maybe doing something slightly chaotic compared to, you know, it's not always that predictable as it comes out of nozzles, and the velocity of the UAVs and things like, you know, their positioning accuracy and all that. There's all kinds of things that would create unpredictability. And the ambition of the studio is that those real-time logistics do actually matter and play a role in the creative process. So I completely agree with the comment, and I think they would too, yeah.
There's something at play where you foregrounded the additive parts. What I think was really potentially very striking about your project is that it's both subtractive and additive. And so, for example, how someone would actually treat sight, or the sight works, could start to create conditions that would allow the machines to operate better. And so, for example, understanding the environment, the prevailing winds, creating artificial boundaries, because material, you don't have the same material contingency that others would have, because material in some sense is for free. But the response in terms of creating the climate, like the microclimates to allow these machines to operate, as much as to allow people to inhabit, I think is something that you guys should really explore. And it is between the subtractive and the additive, which I think that domain starts to really be a very important component. So I wouldn't undermine the subtractive element, because to be honest with you, that sets the terms in which you can kind of cope with this extreme nature. If it's completely tabula rasa, and these guys are kind of floating unprotected, then you know that shit's gonna hit the fan, as they say. But if you create an environment where these kind of things are actually creating, even just with simple partitions in a sense to block some of those winds, then you know that the speed could be much more accelerated. It won't be so dependent on all of the environmental strength. And I just think as a project, it makes an amazing argument to find those fitness criteria which are real time and by necessity are production oriented in the way that you guys are approaching it, which is a very fascinating world to be in.
I want to add something also in an other direction, which is that this material that I have here in front of me is a material that is a substitute for ice, yeah? So while that model is melting, this one is not. So what happens is that I think that, yes, one application of this project is in extreme environments, and totally I think that then the extreme environment, one should deal with it, both in positive and negative senses. But also another application of this project is this one, where it doesn't melt. So I think that the same kind of conversation could happen in this domain, which is the idea of the porous structure that is finished, or you know, where nature collaborates to finish it, etc., is equally present here, and it could happen in an environment in which the drones are flying well. It could be a more controlled kind of environment, but still the architecture that comes out of it is a plausible conversation. I don't know if this is a phase-changing material or not, but still I think there is a lot of room for the project to explore different avenues.
That's perfect. This conversation is as perfect as it can get, because in some sense we don't want this to come to a closure. Like, you have different possibilities of trajectories, and I think that's the openness now where if you are rigorous through this, now you have affordances that will allow you to sort of find ways to implement. You don't need to wait for some future scenario, but you do have to start to consider that if it is something like what Martha is saying, then you have to interrogate what those phase change materials are. If it is ice, and I think ice is a really interesting thing because sodium acetate has its constraints, but the ice stuff is something where this kind of system would actually really start to work. And I would take Philip's point to go and visit them in Zurich, and why not? Make something. Let's do it. Can we leave it there? Okay.